Good afternoon. So this is my third lecture and second lecture on Bluespec. And this lecture has two very distinct parts. So first part is almost a continuation of what I talked about last time, but now I want to also bring in parallelism, or what does it mean to execute multiple rules at the same time. And finally, in the last half, I'd like to spend time explaining the semantics of Bluespec. What are we relying on when we do proofs on this? The whole theory is built on one rule at a time semantics. Okay, so let's look at this very simple example. This is a very, very simple pipeline system where you have three combinational functions, F1, F2, F3, and you're just passing tokens from one to the other. It's extremely easy to describe it using these three rules, which take the first element from in queue, transform it using F1, and stores it in the queue for the next stage. And the second rule takes something out of FIFO1, transforms it, puts it in FIFO2. And similarly, the last third rule takes something out of FIFO2 and does it. So you would agree that this is quite straightforward to write. I mean, this description is pretty straightforward. Just to make sure that we haven't forgotten about implicit guards. So when can rule for stage 1 execute? What are the conditions that have to be satisfied? There has to be space in FIFO1, right? And there has to be some element in queue. It cannot be empty, right? So as long as those two conditions are satisfied, then you can execute this rule. The question we want to focus on in today's lecture is, can these three rules execute concurrently? Can they all go at the same time? Seems like it, right? I mean, as long as you have some token, in the queues, it should be possible to execute it. Fire all three rules simultaneously. But in order for that idea to work, it must be possible to NQ and DQ from a FIFO simultaneously. Because if you can't do that, then these rules cannot execute in parallel. Yes? Very good. Okay. And just before I go any further, 1 second, I think you will say that this is hardly a pipeline system if these rules can't fire concurrently. I mean, yes, one rule at a time semantics is great, but really from a hardware point of view, you want them to go ka-chunk, 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 right? They must all fire at the same time, because that's what we mean by pipeline systems. Yes?
Current rules are checking ready flags on FIFOs.
Right. Mm-hmm. That's implicit checking going on, right?
They're not checking the state of the FIFOs permanently.
That's right. This is the ready wire coming out. Yeah, exactly. So we do not get inside how the FIFO is implemented, right? We're just looking at the ready wires. But now I'm saying we need to find out something more about the FIFO. We need to know if NQ and DQ can be invoked simultaneously. Because if they cannot be invoked simultaneously, then this is not the code we want. Or this is maybe not the FIFO we want. Okay, so multi-rule systems, right? Most systems we saw last time, actually, even if they had multiple rules, those rules are all mutually exclusive, right? So now we are interested in systems which have multiple rules, but many rules may be enabled together or can fire concurrently, right? So what we want to do is we want to talk about such systems. And the questions we want to ask is, under what conditions, when you have multiple rules which are ready to go, they can actually go in parallel, right? What are the conditions for that? And the second thing we want to know, what does the synthesized hardware look like for concurrent execution of rules? What has changed? What's new stuff we need in order to implement concurrency properly? So this is the highest level semantics of Bluespec informally, right? This is what I refer to as one rule at a time semantics. Select a rule to execute, right? Compute the state updates and update the state, and then just keep doing it repeatedly. And the thing to remember is this is a non-deterministic choice when a rule to execute, because there may be many rules that can go on, but you select one of them, and it's conceivable when the selected rule executes, it may disable the rules that were ready to go, because there can be all sorts of dependencies. Okay, but the semantics says that whatever behavior we see in the system must be explainable as if rules executed one at a time. Any order, we don't care what order, but some order they executed one at a time. Rule firings must be serializable, right? That's the idea. Okay, one rule at a time semantics and illegal behavior of a Bluespec program can be explained by observing the state updates obtained by applying one rule at a time. And of course, from implementation point of view, from performance point of view, we want to execute multiple rules at the same time. So when can we do it? We can do it as long as we don't violate one rule at a time semantics. So let's get into that. Okay, so let's talk of concurrent execution of two rules. Two rules can execute concurrently if concurrent execution would not cause a double write error. What's a double write error? Right, if two rules are writing in register X, we obviously have a problem. You have to make up your mind, right? What value you want in register X. Okay, and the second condition is that the final state you get to must be achievable by going either this rule followed by that rule, or that rule followed by this rule. Okay, something like that has to be true. Okay, so let's do some back of the envelope kind of questions here. So I have a rule here, y gets 3, x gets 5, x gets 7. What can you say about this rule? Because you're assigning to x twice, right? So it's a double write error, right? This rule makes no sense to us. All right, what about this one? Y gets 3 if B, x gets 7, else x gets 5. This is okay, right? Because you write in y once and you write in x once. Whether you write 3 or 5 is a different matter, right? So no problem here, right? No double write. In this case, what about this one? X gets 5, if B is true, then x gets 7. There is a possibility of a double write, right? If B turns out to be true. And when there is a possibility of double write, that's as bad for us, right? So possibility of a double write. So the reason I'm pointing out all these things is parallel composition of actions and consequently a rule containing it is illegal if a double write possibility exists. And compiler will reject this. So you don't have to worry about this. If you wrote bad programs, compiler will come and say illegal rule, right? Because it checks what's going on. Yes?
How about possible rewrite this condition like the if instead of B talks about Y? Oh, that's okay because it uses the old Y.
Exactly, because we always read the old values, right? Because whatever a rule does is visible only after the whole rule executes, right? Okay, so I'm going to test your knowledge now by looking at these various examples. Let's look at example 1. Rule RA is x gets x plus 1, RB is y gets y plus 2, right? So let's look at their execution. If you executed both of them simultaneously, what will happen? You know, I initially assume value 0, 0. So you will get 1, 2. Y gets y plus 2, right? Right? Okay, now if you suppose executed RA before RB, what will you get? You'll still get 1, 2. Right? In the second case, you'll get something else, right? So on. You can work this out. This is very simple exercise. I mean, what I'm doing here is, here there is no interaction between RA and RB. Here I'm reading Y, here and updating X, and here I'm reading X and updating Y. And in this one, I'm reading Y, updating X, and I'm reading Y and updating Y. Strange kind of interaction in the last one. But if you just look at, if I executed RA before RB, in this case I'll still get 1, 2. In this case, what will I get? 1, and then 3, right? And in this case, I'll get 1, and this doesn't use X, so it will be 2. And suppose I executed RB before RA. Okay, you can do it. The main point I'm trying to make is this, that this is equal to this is equal to this. So as far as we are concerned, there is no conflict. These rules can clearly execute in parallel. What about the second one? This is not equal to this, and this is not equal to this. Therefore, these rules conflict. All right, what about the third case? This is okay, but so you can say it's okay if you executed them in parallel, because it will behave like as if RA executed before RB. Does everybody get it, right? It's okay to execute them in parallel because the resulting behavior can still be explained in some sequential order, which is RA executed before RB. Are you with me on this? Fantastic. Okay. Now, the way I'm going to summarize all this information is something called a conflict matrix. So you can just imagine I'm going to look at things pairwise, right, and have some things. So I'll say, based on the analysis I did, that if I have rule RA, RB, RA, RB, so if I want to execute RA with RA, it will be a conflict. This is okay if RB can be executed before RA, but if RB and RB executed, it will be a conflict, right? Rules can't execute concurrently. RA less than RB means rules can execute concurrently. The net effective as if RA executed before RB, and similarly for the other sign. And conflict free means rule can be performed concurrently and the net effect is the same as if both rules, in both rule orders. So here you see it's all conflicts, and in this case it will behave as if RB happened after RA, right? Does the idea of conflict matrix make sense? Good. Now, what I want to do is, yeah.
Before executing all these roles, we will start with a figure of the dependency between the data and calculation.
Exactly. So that's what I'm showing you now. So let's first worry about, remember, the question we are after is, can NQ and DQ be done together, right? So let's extend this idea of conflict matrices to interfaces. Okay, so conflict matrix defines which methods of a module can be called concurrently. So what is the conflict matrix for a register? Can you perform 2 reads concurrently? Yes. Can you perform 2 writes concurrently? No, so that's clearly a conflict. And when you, in the same clock cycle, you read the register as well as write it, what is the effect? You read the current value and the write value will appear in the next cycle, right? So that's like saying that read happens before write. If you do them simultaneously, the effect is as if read happened and then write will happen. Okay, 2 reads can be performed concurrently, 2 concurrent writes conflict, are not permitted, and read and write can be performed concurrently and behaves as if read happened before the write. Conflict matrix of a register is used systematically to derive the conflict matrix for any module, right? So it's a bottom-up analysis, that we will do here. Okay, let's take a few examples. So here is your FIFO element. So what can you say about, we have a bigger problem here. NQ and DQ have predicates, have guards, which are mutually exclusive. V is either true or it's false, right? Which means either you can do NQ or you can do DQ. Oops, so this is absolutely not going to work for us because we wanted a FIFO where NQ and DQ can be done concurrently. Here they will not even be enabled concurrently, right? If one is enabled, the other one is not. So, if you draw the matrix, it'll be something like this. The FIFO is not useful. This FIFO is not useful for implementing a pipeline system. So our code was very good, for pipeline system. Unfortunately, the FIFO turned out to be lousy, right? So now we are in search for a FIFO, which can do NQ and DQ properly. And somebody says, man, you were cheap. What is this 1-element FIFO? You should at least have 2 elements in your FIFO. All right. Okay, so let's have a 2-element FIFO. And what we'll say is that in the canonical representation, if there is only 1 element in the FIFO, it'll sit in DA. All right, it'll sit in the right-hand side one. This is just an arbitrary choice. We'll put it in. Yes? So initially both are false. First, NQ will store the data in DA and mark VA true. Okay? NQ can be done as long as VB is false, and DQ can be done as long as VA is true. Okay, let's write down some code for this. So now, please instantiate those 4. Oops, I forgot to instantiate them. This is the PowerPoint problem. But imagine 4 registers, DA, DB, whatever, right? VA, VB, etc. So does NQ make sense? As long as VB has space, as long as VB is false, you should be able to put data into DB and mark it true. And what does DQ do? As long as VA is true, that means there is some element sitting in VA, right? So you can read it. Very good. And first, as long as VA is true, you can read it, return DA from it. Okay, but what is the problem now? So you will NQ something. Now, what will we sense in DA at that point, or VA? It's still false, right? So I need some rule for moving things from DB to DA. So I'll call that rule canonicalize. And I really did forget to instantiate. So just imagine those registers have been instantiated. Okay. So what does this rule canonicalize? Right. So it's saying if there is something in VA, in the A slot, and nothing in the B slot, then please move it. Right? So as long as VB has something and VA has nothing, then DB gets to DA, VA is true, VB is false. Okay, if you do this, now tell me, can both NQ and DQ be enabled together? Yes, right? They can both execute concurrently. But neither NQ nor DQ can execute again until canonicalized rule fires. Right? Because yes, I did NQ and DQ, then from outside I can't tell anything, but internally something has to happen, some transition, before I can NQ and DQ again inside it. Is this too mysterious or this is making sense? Okay, enough you are shaking heads that I believe it's probably making sense. All right, okay. And if you draw the conflict matrix of this, this is what it'll look like, that NQ and DQs, etc. are all conflict free, and first always has this relationship. First always behaves as if it happened before DQ. We read it first, then whatever we DQ will be visible only in the next cycle. Many other FIFO designs are possible, right? So not quite 23, but we can get there if you want. Right? Okay, so if you look at this one, this is called a pipeline FIFO. One can NQ into a full FIFO if the DQ is done simultaneously. So you think it's full, but I promise you, while you're trying to NQ, I'm also trying to pull something out. So if you are nimble enough, right, you should pull it out and I'll put the new value in. Okay, so that's what this is reflected in this conflict matrix over here. You could have had a bypass FIFO, right, where the values just fly through. You put something in and instantly, the DQ can also see it. There are many situations where you need such a FIFO. Now, designs of such FIFOs requires another kind of primitive element, which I call EHR, for ephemeral history registers, a mouthful, right? But essentially it's a register with a bypass. And unfortunately, I don't have enough time, to describe, how the hardware for this will work. But from your point of view, I'll just give you the conflict matrix for EHR, which is somewhat different from an ordinary register. And then you'll be able to build these kinds of FIFOs, from it. Okay, so I think basically what I've shown you is that functionality can be the same, right? FIFO functionality, if you want to write some axioms at high level, what value you get by dequeuing and queuing is exactly the same. But there is differences. There are differences which are not captured by types. These differences are coming from implementation, but they can be abstracted out in terms of a conflict matrix. So often when we design, we don't worry about conflict matrices. We worry about conflict matrices only when we start using a module. We say, oops, I don't like this. I wish this thing, it had a different conflict matrix. And then there are systematic ways in going and changing your implementation so that it will allow concurrent execution of things and so on. Okay. So what I want to just briefly give you a glimpse of is how hardware generation is affected by this conflict information. Okay, preliminaries recall from last time that BSV compiler generates a combinatorial circuit for each rule and each method, right? A rule rule or method sets register X when it must generate both the data and enable signals. So in this example you are seeing you have rule foo, which has a guard P of X, and if the guard is true, then you will go and set X equals F of X. Does it make sense? Right? Because register X is somewhere out there, and its data value is F of X, right? And its guard value is, its enable signal is whatever P produces. So if P turns out to be false, then nothing will be stored in the register. Similarly for each action method and action value method, etc. So I need to introduce just a teeny bit of notation here, and I hope this makes sense. So I'm going to give you a special kind of mux here. Remember, in our formulation, every data line has a associated valid bit, whether this data means anything or not, right? So here, so I can mix them together and say, oh, X gets either this or this, V gets either this or this, depending upon which one is true. And if both are true, hell will break loose, right? Then this idea won't work, right? So in some sense, when we merge two or more values, at most one VI should be true at any given time. This is often referred to as one hot encoding. So you have a mux with n lines going in, right? But only one of them, at most one of them can be true. At most one of the VIs can be true, okay? And of course, all these things must be of the same bit width. That will be, all this is being enforced by the compiler. It will make sure that only one of the lines is true. One of the predicates is true. Only one of the VIs is true whenever it uses that kind of thing. All right, so let's look at this example. So what do we have here? We have a method action F, which is X gets X plus A, and action G, which is X gets B. All right? So these things clearly conflict with each other. Can I generate the circuit for F? Yes? Circuit for G? Right? I mean, that's for rule action G. But the problem is they have to be brought together because they're both trying to update X. So I put in something like this, and then I can. Now, this circuit is wonderful as long as either F is going or G is going. Because if somebody enabled both of them, well, then you'll get a double write error because both will be trying to write in X. So I did analysis for you earlier showing that these rules conflict. So this is static thing that is going on. I can look at rules and say under what conditions, they will, if they can ever conflict, then they conflict, as far as we are concerned. How does the compiler ensure this? CM to rescue. CM for make show that methods of F and G conflict and should never be called together. So compiler is taking the responsibility of generating this stuff for you. Okay, so now let's see how, this is clear. Now what we want to show you is, suppose you make this module, make this example, right? If I wrote a rule like this, what will you conclude? So in this rule, you're calling the method of, you're calling F and G both, right? That's not allowed. Why not? because F and G conflict. So any such use will be flagged by the compiler as, sorry, RA is an illegal rule. Makes no sense. All right? Suppose you have two different rules, RB and RC. One calls F1 and the other one calls G. Conflict matrix will show that these rules conflict with each other, because if you try to execute these rules in parallel, then they'll both try to do it, right? So RB and RC should not be scheduled concurrently and executed one by one. Okay, so just to close the whole loop here, how do I do this? So here is my black box matrix, not matrix, module M, which has two methods, F and G. What extra information do I have about F and G? That they conflict, right? So conflict matrix tell me, please don't call them together. All right? Okay, so can I generate the circuit for RA? Pretty straightforward. I can generate the circuit for RB like this, and suppose I take the ready signal, whenever this rule is ready to go. Okay, and you'll do the same thing here. So far, so good. This circuit will execute rules RA and RB concurrently. This circuit is correct only if rules RA and RB do not conflict. If they conflict, then this circuit is meaningless. So let's deal with the difficult case. Suppose RA and RB do conflict, then what circuit should be generated? Any ideas what circuit should be generated in that case? Pick one, one of them should go, right? Either RA or RB, but not both. So the question is how? How to do this? So I'm going to have a scheduler. This is a dynamic scheduler. I'm building a circuit for you, in which I'm going to feed in the guards of all the rules. So I'm saying, oh, these are the guys who are ready to go. So if GS1 is true, that means rule 1 is ready to go. It's called, also known as can fire signals. So this is telling you this rule can fire if you want, right? And what comes out of this is will fire signals. You say, yeah, you may have been ready to go, but I'm the controller. I tell you whether you can go or not. All right, so guards of many rules may be true simultaneously, and some of them may conflict. So BSV compiler constructs a combinatorial scheduler circuit with the following property. For all I and j, if will fire signals are true, then the corresponding must be true, and rules ij must not conflict with each other. Your intuition will work on this. So just imagine you have n rules coming in, n signals coming in, and statically you have been told these conflict. So all you have to do is build a circuit, which takes all the conflicting ones and picks out one, from them. So now let's see what we would have done in this simple example. We'll take this, and scheduler is generated based on conflict matrix for RA and RB. So we take this signals and feed it here. That means they're ready to go. If they're not ready to go, there is no problem. If only one of them is ready to go, corresponding signal will always be true. But now what the scheduler does is, it says this rule will fire, this rule will fire. So you can imagine all the permutations and combinations for this. It's just that it's being done by the compiler. So this is a very interesting example of something. Scheduling decision is being taken every cycle. Every cycle we are looking at which rules are ready to go. And then we let as many of them as possible go, provided they don't conflict with each other. And the set of rules that don't conflict with each other is not unique, right? You can pick a maximal set or something, because this is a highly non-deterministic system, right? Generally, a scheduler has very small number of gates, right? It gets optimized away, right? A correct but low performance scheduler may schedule only one rule at a time. You can always do less. You don't have to try and execute every possible, rule that is ready to go. But that's what the Bluespec compiler does. It tries to schedule as many rules as possible. Have you gotten the idea behind this? What's happening in this? Okay, so a more complete picture of this is that, you have muxes over here, and this will, come out from here. They're all trying to update their thing, and scheduler has to make sure if two things are trying to call method F, only one of them will go. I was showing you that example with registers, but this is just as easy to understand. Again, if the scheduler is implemented correctly, it is guaranteed that only one of the inputs to the mux will be true. So it has to do one hot encoding. Okay, so the takeaway from this part is that one rule at a time semantics are very important to understand what behavior the system can show. I mean, that is the bedrock on which all the ideas are being built, that even though this is a very complex system full of hundreds, if not thousands of rules which may go on concurrently, right? But if they go concurrently, then they don't conflict with each other. And it's a very dynamic situation, because after every firing, different set of rules are applicable. Okay, efficient hardware for multi-rule systems requires that many rules execute in parallel without violating one rule at a time semantics. Okay, BSV compilers builds a scheduler circuit to execute as many rules as possible, okay, concurrently. So this completes the picture that what this tells you is when you get into complex designs, first you're just worried about correctness. And the correctness level, you can just think of one rule at a time, one rule at a time. All the theorem proving will work using one rule at a time. Once that happens, then you say, I could have done a slightly different implementation, which would have given me this kind of conflict matrix for this module, and then I have more concurrency. Right? So completely different phase of design. First, you must get it right, and then worry about performance of it. All right, so any questions about this part? Because now my tone will change after this.
So does the logic of scheduler changes with each matrix, conflict matrix, or is it same?
No. For each conflict matrix, you will have a new scheduler, right? So, yeah, if you change any conflict matrix, the scheduler has to be redone at that point. But it's completely automatic. It's completely automatic, and believe me, the compile times for this do not dominate. Scheduling part is not the most expensive part in BSV compiler. Okay, so now let me talk about the semantics of Bluespec. So first of all, a Bluespec is a, yeah.
Just to get big picture of what we have discussed previously. So we have a program. This
Yeah.
program has been, compiler has taken this program and generated machine instructions.
No machine instructions. It's directly generating this hardware. So it's generating a description of this circuit, and circuits at this level are known as RTL, Register Transfer Language.
I want to connect this hardware with the programs which I'm writing. So, am I?
I think you are thinking of programmable hardware. I'm not talking about programmable hardware. I'm talking of special purpose hardware so far. right? I'm talking about hardware which just does GCD, which just does F and G, right? Just does my example number 3, right?
But this is how programmable hardware is also generated.
No. So programmable hardware, if I was building a programmable hardware machine, yes, it'll have many modules. It'll have an instruction fetch module, and it'll have caches, this, that. It'll have branch prediction. It'll have reorder buffer. It'll have an ALU. It'll have a memory system. Each one of them will be designed, and my specification for that is not the programs that execute on it, but did I implement the ISA semantics correctly, right?
You will generate the enzyme, well, actually, the Verilog that describes the entire.
Exactly. So you will be writing that processor in Verilog, and the design you write is completely different if the processor is very wimpy. I mean, it's a processor intended for IoT applications, versus it's an in-order processor, versus it's an out-of-order processor, versus it's a multi-threaded processor, it's a multi-core processor, right? So,
It is complicated, but the blue picture, if we see, it's built on this basic idea how we are generating.
exactly. So what I'm describing to you is a language for describing various hardwares, right? What software you run it is exactly what you would have done before, right? Actually, that's one reason I wanted to do this, because in just about all other things, what you've been hearing is you have some high-level specification, and you ultimately generate instructions from programmable hardware. This compiler is taking some high-level description and actually generating hardware itself. This, but believe me, I mean, for the first time, I taught it to introductory class last time. There were 80 students. And the problems I encountered were some that I had never faced before, right? So only requirement for this course was that they should know some Python. So just to make sure they know Python, we give them a lab 0, right? GCD, right? And we give them some binary arithmetic, etc. Then after that, I have taught them sequential machines, and I say, okay, now go and implement GCD. They say, yeah, syntax is different, but it's quite easy, right? I just fed this GCD code and gave me the right answers. Oops, no, that's not the point. I mean, the fact that it simulated your GCD and gave you the right answer is a big bonus, but that's not the goal. The goal is to see what hardware came out of it. And for them to understand, that is something completely different takes a while. Now, if this confusion wasn't enough, after a while we say, okay, now we're going to design programmable machines. So we make them write GCD in RISC-V assembly language. They're saying, oh, okay, right? So this is different formalism, they write it. And then guess what? We build RISC-V processors on which they run GCD. So it's really, I mean, for introductory class, understanding these different levels of abstractions requires some effort. Okay, so Bluespec is a classical 2-level language. So the basic part of it is this rules and actions that I've been talking about, right? And this is the work that James Ho and I had done. That was his thesis, so circa about 1997 to 2000, that's when we were doing this. And we showed that we can actually generate very good circuits, using this kind of source language. I mean, the language was very, very primitive. We used to use term rewriting systems of some sort. Okay, so later on we renamed it guarded atomic actions because it's really a transition system because the state remains fixed. There is no dynamic allocation of state in this machine. But the biggest advancement came when Lennart Augustsson, who worked for this company I had started, designed this language called Bluespec. So this was a modern language with objects, types, higher order functions. And it was not exactly an embedded language in Haskell, but it was really, everything was done in Haskell in this. So everything was a monad. right? Actions were monads and modules were monads and, you name it inside this. Okay, then I decided to start a company, to sell this tool in 2003. So this is a different company than Sandburst. And the first meeting I had with VCs, venture capitalists, they look at this and they say, what is this? This is Haskell syntax. That stuff, by the way, is now known as classic Bluespec. Right? So it had Haskell-like syntax, and I'm getting nowhere. So, one of my friends, after hearing the talks at some company, says, Arvind, man, I don't do Haskell. So I said, what do you mean you don't do Haskell? He says, I don't see movies with subtitles. To him, functional languages were like, it's not a question of whether I can understand it or not. I just don't do this, right? Why can't it look like C, right? Whatever you're doing. You can give it new semantics if you want, right? But it should look like C. That's how System Verilog was born. So System Verilog was a language which was new at that time. It had much richer type system. And then we took and did a real surgery on it and changed the surface syntax of Bluespec completely and made it look like System Verilog. And it had immediate impact. All the questions about syntax went away. So it's not that people understand rules and actions. They say, oh, yeah, something. Yeah, C-like. Okay, good, right? Or Verilog-like, something, So people's intuition is built. And, until it's, I can kind of appreciate it. I mean, if somebody started speaking German to me, and I wouldn't understand a word. So I think for many people, syntax is like that. You show them Haskell syntax, and then say, no, don't do that. Okay, but the most important part of this is, so at high level, we have an ultra-modern language. It had all the features that you can imagine, you would expect from a higher order functions, very strong type checking, et cetera, Then, because this is a hardware language, he did a massive partial evaluation, static elaboration, so that ultimately you end up with a straight line code of the kind I have been showing you. Rules, module, right? So what it generates ultimately is a collection of modules. So that's the massive partial evaluation phase. And that's the part that takes maximum amount of time in compiling. So if you start using very sophisticated features of functional languages, right? It'll take time to it's like executing your program at compile time. The way I explain this is, at compile time, what you're doing is you're inlining function calls and unrolling all loops in this language, right? Instantiate modules with specific parameters that you have for them, resolve polymorphism, overloading, perform most data structure operations, because there are no data structures in my language except for, bits and primitive things like integers and whatever you define using those. So this is how I like to explain it. This is, for this audience, you're too sophisticated for this. But in software, when you give me a source program, I compile it and I get a .exec file, and then I can do many runs on it. I give different parameters and I run it, right? When you are on the right-hand side, you divide the parameters into two parts. So there are lots of parameters, each one of them results in different design. And then once you have the design, then you can again give runtime parameters and run it and generate many things. But what we are studying, our goal, our metric for judgment is how good are these designs? Design 1, design 2, design 3, which one do I like? Which one meets my performance criteria? Which one meets my area requirements, power requirements, and so on? Okay, so this is the slide you had seen earlier. And what we have to do is, for theoretical purposes, for semantic purposes, for proof purposes, I only have to give you the semantics of one rule at a time. What is the behavior that is possible if I execute one rule at a time? Then I'll prove a separate theorem about my compiler that when it does multiple rules, it doesn't violate this. I'm not going to do that, right? So just let's try to understand one rule at a time semantics. Okay, so this is my kernel language. Let's see if people can read this. Is the expression clear? It has constants, it has variables, and it has operators, like plus, etc. And my actions are, this is a register read, so R stands for a register. In my module, see, there are registers with initial values. There are rules with name S and actions associated with them. And there are method calls, right? This is my interface methods, Fs of various sort. And I can put as many modules together as I want, so that's why M plus N over there. Okay, so now look at this. I'm using monadic kind of syntax, so I always end in action here. So, you're doing a register read, putting it in X, and now that X should be used in A. All right? Here I'm doing a register assignment. So R is some register in which I'm putting E, and that has to be done. But remember, A cannot see the effect on R. It can only be seen in the next cycle or something, right? A is still evaluating using old values in this. This is not a function call, this is a method call, right? So now F is method of some other module you're calling, right, in this. And whatever result you get from it, you will go and use it in A. Conditional, I've just shown one armed conditional. If E, then A, otherwise it's a no op. And you'll just do A in this. This is the equivalent of a guard. So you're saying if this guard evaluates to true, it's like nothing, no op, right? Just go into A. On the other hand, if it evaluates to false, you stop, you get stuck. This evaluation is going nowhere in this. And return E is just lifting it back, right, to the action category. Syntax is more or less clear. Maybe as I give semantics, it will become more clear. So just ask questions, right? No recursion, methods of only other modules can be called from a module. So, right, you have many, many modules, and I can call your methods. There is potentially recursion because that guy can call my methods, etc. Okay, so I'm going to give semantics in two different styles for this. So first, I'm going to give semantics which are non-modular. By that I mean I have view of the whole universe. I know what's going on inside every module. And if you think like that, the semantics are relatively easy. And if you understand these semantics, then I will show you how to give non-modular semantics. Sorry, how to give modular semantics, where I can talk about a module without talking about other modules. All right. So I'm going to write down my judgments of the following sort. Let O be all the registers in my machine. Set of all the registers. So this module has 5 registers, this module has 7 registers. Collect all of them. Set O with initial values. Given that, and if you give me some action, I will say, oh, the effect of executing this action is you want to do the following updates to your register file. And you want to return value V. Right? Because every action only updates a set of registers, not all the registers. So you are collecting what updates are to be made. You're not making those updates. You're just collecting all the updates that are to be made. Okay? And V is the value returned by the action. All right, let's see. So what is this saying? This is a register read. So you're trying to read a register R. So whatever value for R you get, right? What is that? That is the value you're taking from register, this assumptions here, and you will go and substitute that for X all throughout A. And if you execute this, it produces u comma v. If that is the case, then you'll say this goes to easy. All right, register right. So I have to evaluate E, right? So suppose that produces VR. And now, remember in A, I can't see anything about R. I can only see old values. So I just take the old O and evaluate A and it gives me UV. Okay, so the return answer is V, but updates, I have to include this update to R. So I remember that R I have to increase to VR. And what is this funny looking symbol? Right. This, I mean, in some sense, just a union, but it cannot exist there before. Right? So represents a disjoint union. Otherwise, it's a double write error. If X was already present, if R was already present in U, then two people are trying to update it, not allowed. Okay? This is pretty trivial. So you evaluate expression E, right? And you substitute that value for X in action A, and you evaluate A, and this is just not a big deal. This is somewhat interesting. Okay, so now I'm calling another method from another module. All right, so first part is easy. I go and evaluate E. That gives me Vy. And what is F? I consult the definition in some other module where F is defined, and it says the definition of F is lambda y dot b, some action. So I go and substitute Vy in B, right, for y in B. And if the evaluation of this results in this, then that's what I have got. Right? So I have U of F plus A is going here, so I mean, you can see just by looking at this rule, this is highly non-modular. Because I was working on this module, you made a call to another module. So what did I do? I immediately went there. I said, what is F? And then I go and evaluate F in that module. And whatever result I get, I come back and resume my computation here. All right? So what happens if the conditional is true? Well, then you evaluate the true side action, and whatever it gets and whatever the rest of the action is going to be, you combine them together. And if it was false, then you don't evaluate AT. You just, whatever you get here is what you return. Assert. If E turns out to be true, then you just go and evaluate this, right? And if it turns out to be false, I don't give you any rules. So you're stuck at that point. This elaboration failed. You can't go anywhere. No, that's not meaningful anymore. All right. And return is simply, lifting it up. So there is no updates, of course, involved here. And it's the end of the story. It's just returning V at that point. Do these semantics make some sense to you? What I have described is how various actions happen. And now, only thing I have to tell you is how does a rule evaluate? What is this saying? So suppose I say evaluate rule S. Well, what you're saying is S comma A is part of, this module M, and A goes to this. And what is this? Now I am finally updating the register set. Does everybody understand this? This is a very important thing, and that's why this arrow looks different. Finally, the transition is happening. This is the atomicity thing. Until now, we were collecting, right? We have collected, all the registers are to be updated, and now we say, to do this rule, following updates result, go and do those updates. That is the execution of the rule. I hope this transition makes sense. This is the only state transition, right? Everything else was just building towards it. And now I can talk about what does it mean to apply rules repeatedly. Right? So now O's represent sequence of state changes. So suppose so far I have observed the following change. I started with this initial state, and currently I am in state ON. Okay? And now I take some rule here which takes me to state ON plus 1 according to the rules given earlier. So then I'll say this state I have extended the sequence by one more. So first we saw actions, which told me the updates that need to be made. Then we saw a rule which tells me make the update. And now we are seeing sequence of updates, right, to the state. So you're building a history, of things. So it's not, by meaning of a module, meaning of the system, because I'm looking at all the modules together, is the set of all the behaviors given the initial register values. So if you seed it with something, you're going to see all these different things coming out of it. And whatever you see there is. Okay, so now the thing we are all after is sort of, if I want to refine this module, if I want to say M1 is less than M2, then it must be the case that the behaviors that M1 exhibits is smaller than the set of behaviors M2 can exhibit. Because our system is highly non-deterministic, and ultimately the hardware that will be generated will be absolutely deterministic, right? So it's picking some behavior, for a given initial state. If two sequences contain the same final state, given the same initial state, we treat them as if they're congruent with each other. So a system is deterministic if all its behaviors for a given input are congruent. This gives you some hint of the semantics of this. Is this kind of meeting your intuition about this atomic rule stuff with guards and so on? Okay, how much time is? Few more minutes. So I'll just do now modular semantics. Okay, so modular semantics is pretty recent, right? And this is what is being used in the Kami system that Adam and Murli and other students have built, a proof system in Coq for proving the correctness of BSV programs. So there we are really after modular semantics, because we are after modular refinement. If I change part of my thing, I want to say my whole system still is correct. So how do I formulate this problem? So that's what I want to show you. Okay, so this we already discussed. This was the non-modular part, right? That when I made a procedure call, method call here, I immediately went and looked inside the other module. To give modular semantics, I know nothing about F. So how should I proceed? We need to assume the results that will be returned by F. We're going to go to a relational framework, right? So instead of actually seeing what f does, we say, well, let's assume f of x will return y and take it from there. We'll record it in a label, and later we reconcile labels when two modules are put together with each other. So, when you do symbol manipulation, you say, this looks exactly like before. All I have done is I've added a label in the end, right? Okay, so labels are coming, but just imagine now, in addition to the updates, I also give you a label every time, okay? But one difference here is that O will only contain the registers of this module, not all the modules, only of this module, because different modules have completely disjoint set of registers. Okay, so register update. This is same rule as before, with L written at the end, same rule as before. This is the one that is different. So what are we doing in method call? Okay, we can evaluate E, right? And now we can say, suppose, just imagine as if the f must not be, it's a foreign method. That's why we don't know the body of it, right? And let's assume that when I apply f to vy, it returns vx. This is an assumption. This is a free variable at this point. So I'm recording this triple, f, vy, vx. This method call, when made with this argument, returned the following result. And this is my label, right? So whatever labels I had until now, I have added one more label to it. Okay, so what do I mean by disjoint set of labels? Once somebody calls that method f, nobody else can call that method f. Remember, these are the dynamic semantics. We are executing it, right? So don't get confused by all the muxes I was showing you. That's a compiler's job. Here we are talking semantics. So in semantics, if somebody calls that method, then obviously in the execution of that rule, nobody else can call that method. So in the labels, we are recording which methods are being called, so no method can occur twice. So that's why it's a disjoint set. If you call the same thing again, it's like a double write error or double method call error, if you want. All this is exactly the same as before. I've just added labels everywhere. Yep. Sorry? Okay, so I think the only rule I'm really changing here is this one. So remember, in this one, I was unable to do f of x. If you go back and look at the rule, what we did in non-modular semantics, we just evaluated f of x, right? We substituted it. We can't do that. So I'm saying, okay, so it's a promise that if I send argument x, the result I get back is vx, right? I send vy, I get back vx. So this is the thing I'm recording. It's like an assertion. It's like a constraint that whenever it talks to that module, that better be preserved. That's all. So all the external calls I encounter during my execution, I just keep recording them.
What role label has played?
I haven't shown you what role it has played. So far, we are just collecting. We are recording all the things. But I think the important thing to understand is what this means is you really can't compute, because you don't know these values, right? So it has become a very different system. It's not at all like the operational semantics I was giving you earlier, right? So this is some relations you're creating. But mechanically, just, This is the only place where anything happens with labels. All right. Now, what I want to do is, I want to do one rule at a time, right? So this is a trick I play. So suppose you execute a rule, and rule says, oh, updates U and L. So I'm adding this special label to it. Guess why I'm doing that? If you have chosen to execute one rule, now you can't execute any other rule. Because the moment you try to execute any other rule, it'll also have a dot. And then you can't combine the labels. So this is just a trick to say that you have only one rule executing at any given time. Okay, so far I was looking at this module and I picked a rule and I said these are the labels it can build. But this module also has incoming method calls, right? So let's see what happens, when you call one of those methods. So for incoming method calls, right? This is one of my methods, f lambda xa. So, and I can have many of them, right? Because many methods of mine can be called simultaneously. So for each one, what I'm doing is I'm saying f of x, and this is very interesting now. I don't know the value of f of x because that's coming from outside. But given that, I can compute the new value, and that is v over here. So now I say, this is my method, so I'm calling it f underlined. This is what I will do. And it got the value vx, so this is the free variable here, and v is the value that depends upon vx over here. Does it give you a hint as to what's going to happen? Outgoing method calls were f. Incoming method calls are f underscore, right? So when you match them out, I think that's what. So now I have two modules, M1 and M2, right? And M1 can go to U1, L1, M2 can go to U2, L2. And what I want to say is, this transition is possible, I want to do something like this. So I have to explain what I mean by that. So what does it mean? When is this allowed? When can these modules communicate? If there was a method call in L1, which was referring to M2, then I must find a method call on the other side with underscore, because that is the value it's going to generate. So they're going to annihilate each other. This was an assumption until now, and that assumption is being resolved because I'm giving the value x, and I'm expecting those guys to return the value y. That was the assumption in generating U1, L1. Right? So as long as those things match, and you have to do it the other way too. So two labels, when they come, if they are compatible, then we say, wonderful, you can do this transition. And by the way, all the things that have been discharged, we throw them away. So he says, L means that L1 plus L2, where all the matching labels from M1, M2 have been deleted. Do people get the intuition behind it, right? That we have found a way of giving semantics to each module. And now what we are trying to do is give semantics to, so that when we match them, right? And these are still transitions, no state change is taking place, right? This is just, if these were the updates, then these will be the updates, something like that, you're saying, when two modules communicate. Okay, but sooner or later we have to do a real state transition. So what will happen in real state transition? You have this, right? And suppose you apply everything, you start with some rule, and you sooner or later discharge all the methods. If you have discharged all the methods, what will be left in the label? That single dot, right, will be left because everything else has been annihilated. That means this rule has executed now. Now I can take all the U's and go and update the local state. This is exactly how BSV hardware behaves, right? A rule may go all over. It calls this method, that method. You can call methods all over the place. But state change is all simultaneous. At the end of the clock period, all those registers will get updated. That should have been updated, which may be spread across many modules. So this is the thing which takes a while to understand, that it's a very peculiar combination of asynchronous things, because we really don't talk about time. And yet, because of atomic rules, you have very strong control in saying this X can be updated only when that Y is being updated, right? Because that's what atomicity is guaranteeing you here. Behavior sequence of state changes. This is not interesting. So now you can think of vectors of state, in this. Okay. Oh, sorry.
In a couple of slides before you
Yeah.
said, as long as the labels match, you discard the labels.
Yeah.
But what if a module is generating a value which is used by multiple modules or vice
Not allowed, because they will all be different method calls.
No, that would be same method call, let's say.
I don't understand how. So suppose you wrote a rule here, right, which calls that method G over there.
Yes.
So what do you mean?
Then there is other module which calls same module with same.
Not allowed, right? In the same rule, it cannot happen.
Okay.
That's a property of the language.
Okay.
In the dynamics, of course that method can be called. Maybe it's called by some other rule. But remember, we have already set up the machinery so that two rules can't be called in parallel, right? By using that dot trick over there. Does that answer the... Okay, so this is exactly what you would expect. Now, this is the most important theorem for us. So first of all, label transition. I can't evaluate everything, right? So suppose I gave you just one module in the whole system. But that module, I have given you enough semantics here to describe you what labels can be generated, right? That is the semantics of it. I don't even have to worry about internal state. I say this module can generate the following labels, which has lots of free variables in it because assumptions are involved, right? And if you gave me two modules, where one is the strict subset of another, then it's fair to say that this one refined that one. So very, very different interpretation, very different way of evaluating. But the idea is the same, right? This M1 refines M2 if the behaviors are contained in the behaviors of M2. But the whole reason for doing modular semantics is this theorem. That if you have a system A plus B, right? And I want to change A to A prime, I never have to look at B. I only have to prove that A prime is a true refinement of A. The semantics I have given you implies this theorem. And believe me, we are applying this to very, very heavy-duty refinements, right? We can keep the memory system the same and replace the out-of-order processor with in-order processor without understanding anything about the memory system, right? So when you do very big designs, it's extremely important that you be able to refine some module of it without having to understand all the parts of it. This is what I started out with, when I said in my lectures that what is missing in hardware design? IP reuse, right? Ability to do modular refinement. These are the things I'm showing you that Bluespec supports. very well. It really supports very well. And I don't have to talk about this. Okay, so summary. BS is being used by us and many other companies to design extremely sophisticated hardware. But what other companies do generally is a black box to me, right? So I think Google are the most sophisticated users of Bluespec, but I have no idea what they do. The lips are sealed, even though half a dozen of my students, right, including Leonard, they have finally all drifted into Google, right? So there are quite a few important companies. Intel also uses, Bluespec, but I don't mean to imply that it's in widespread use. So inside these companies, there are very sophisticated projects. Nobody is using Bluespec for trivial work, right? So if they're using it, then they're using it for something very interesting, inside the companies. Okay, there is no discernible impact on the quality of hardware being produced. We have shown this over and over again by our designs, right? But the skepticism remains, right? People say, well, I don't know, well, what? But that's... Adam Chipala and collaborators have built Kamiya system for writing mechanically checked proofs for BSV programs, so I'm closely collaborating with them. I'm very interested in all these theorems, though I don't write down the mechanized proofs myself, mechanically checked proofs myself. I'm still old-fashioned paper and pencil guy. We are teaching our introductory logic design and computer architecture course using BSV. So this term was a trial. Next term, the dam breaks loose, 400 students, right? I have to teach, which means I have to also teach it to quite a few faculty members, because I have an army of teaching assistants and quite a few other faculty members who are involved in this. So people always ask me, so why has Bluespec hasn't taken over? So this is just applicable to most new ideas, right? If you want to change, there is just automatic resistance. Maybe it's just a natural phenomena. But people cannot reject Bluespec on the ground that it doesn't generate good hardware. And this is really the lesson we learned by working for so many years on functional languages. I mean, I love functional languages. I mean, the kind of power it provides, I use it all the time in my work. But I think functional languages conceded too much inefficiency up front. So you can't reclaim it, in some sense. It becomes major headache. And if you reclaim it, then your programs start looking like C programs. You're back to square zero, at that point. So I think Bluespec design from day one was guided by the fact that extremely efficient hardware should be possible, that there is no inherent anything here, logic that is not present already in the designs. Okay, so I will stop here.